let's make a start. So there's afternoon seminars by Alice Thompson from the University of Manchester, where you've been there for what, 5 years or something? 6?
8.
8?
I did a postdoc before.
Yeah, so previously you were a postdoc at Imperial College, I think.
Yeah.
And a PhD student with John Billing at the
Yeah.
Okay, Alice is going to talk about feedback control and control-based continuation of deformable bubbles.
Okay, thank you very much. So you could think of this talk as following on from 2 weeks from last week. So Andrew Hazel talked about bubbles, and Susana Gomez in particular talked about feedback control. And this is feedback control for bubbles, but it has, it's always good when you write a graph and you think, I will combine 2 things I know, like with my 2 postdocs. But it's actually in a slightly different perspective, and it's something that I've been talking about with Alex and others, which the kind of things that Susanna was talking about last week was how to stabilise a falling liquid film, right? So it has really complicated fluid dynamics, and one way you can look at controlling this is to think about a hierarchy of models. You can think of simple models, you can think of more complicated models. And in general, as you get more complicated, you expect that you'll get better control over that physical system. So what we're kind of doing is putting a lot of effort in learning how to control a film or something else. But what this talk is trying to do is to think about a different question, which is how can we use feedback control in particular to help us learn more things than we knew to start with about the system itself. So in particular, what I want to do is use something called control-based continuation, which kind of comes from dynamical systems, is relatively new. It's mainly being used in pretty simple mechanical devices with complicated springs and strings and other things. What I want to do is to think about how we could detect and observe unknown unstable states, or things that we don't know exactly what they are. So if I just want to stabilise a uniform state of a falling liquid film, I can be pretty sure that my uniform film has a uniform height. And it doesn't matter what model I pick, that will always be exactly the same. I could try and stabilise something else. I could think of a travelling wave. And in that case, the shape of the travelling wave would depend a little bit on what model I picked. Or in feedback control, I could pick some completely random other shape and say, I want it to look like the pyramids. Right, I could just pick anything I want, and that would be, we could try and get better at that. But what I want to do instead is just to try and think about how we can, in an actual physical experiment, we could learn using feedback control more about the unstable steady states of the system, or the unstable travelling waves, or something else. So I gave this talk at UEA at the very start of May, end of April. And that didn't have experiments in, and I've slightly reorganised this so that there are experiments and a moving bubble. So there are 2 different problems that I want to try and present side by side. We'll see how unconfusing this gets. Okay, so this is an experimental setup, but actually both of the problems start in the same way. So we take a Healy-Shaw cell, or Healy-Shaw channel, so that's 2 glass plates separated by a uniform thickness. It's about 1 millimetre. And here's my kind of pancake-shaped bubble in the middle. We've got side walls where no fluid can escape, except if I specifically inject it. Then we have some outlets, and in my 2 different problems, they're slightly different. Okay, so in the experiment, well, we need to do something to drive a flow, because certainly if I just leave it like this, my bubble should sit quite happily as a circle in the middle doing nothing. Right, so let's liven this up a bit. Well, here's one option that we actually have in the lab. Here's some experiments. So what we're going to do is inject fluid at 2 points on either side of the cell in the middle. So we're generating a straining flow within this Healy-Shaw cell. And then the bubble, we have a very viscous fluid, we have an air bubble in the middle, and there's surface tension across the interface. And that's all we've got. So this generates a, hopefully, symmetric straining flow. What would you do if you were the bubble? You would, you totally would, right? So there's 2 things that we can see. So here's an experiment. The bubble gets squeezed by this flow, right? So the flow's coming in I guess, here and here. And one thing that the bubble does is it moves slowly, but away from the middle of that cell. And the other thing that we can do is, depending on how unlucky you are, we can break up. Okay, so this is actually a really quite simple system. And you can think about what a bifurcation structure for steady state might look like. Okay, so if I start off with no straining flow, then we're looking at a circular bubble. Okay, that can be positioned anywhere in the cell, right? But if I have a little bit of flow, then it kind of has to be in the middle to be steady, but that's going to be unstable. And then as I increase the strength of the straining flow, it gets squashed, like that one, except imagine those are steady states. So we get bubbles that get increasingly squashed until eventually we reach some flow rate where we can't sustain these deformed bubbles anymore, and then there's a limit point. And sorry that we're going to lose the videos now because they're just really cool. We expect a bifurcation diagram that looks something like this. Except I think like warping in PowerPoint still doesn't go very well. Just imagine that this goes through 0 here. Okay? Circular bubble at 0 flow rate. We'll talk about what we're actually measuring here. But there's a limit point where the bubble splits, and then there's another solution branch that we would hope to get to, and that is what we're trying to do. And, well, what we say about stability? This one is unstable to the bubble translating. This branch up here is also unstable to the bubble translating because the shape deformation that corresponds from moving one to the other is symmetric. We've got a bifurcation between two symmetric branches. So we've got two different instabilities there, one about shape deformation and one about translation of the bubble. So what we're going to try and do, I'll have to introduce my other problem as well, just to keep you busy, is to think about how we use feedback control to observe this one. That's kind of easy. You just need to make sure the bubble moves to the middle. And then how we use feedback control to find that one, which turns out to be harder without being completely rock hard. And then there's another problem as well, which is much harder. Okay, so problem number 2 is this very classic one. So this kind of Saffron-Taylor bubble. So we've got this Healy short cell, it's now very long, and what I'm going to do is, instead of injecting fluid in the middle and then to the straining flow, pump fluid in at one end, extract it at the other, so the bubble moves in general with the flow, but at a slightly different speed. It can deform as it does so. And, okay, so this is all models, but we have plans for experiments, which were PhD student Sammy, who's done all the experiments, is working on this now. He is very optimistic that this will take 2 months to get through. Right, but we're looking at how this bubble moves. And some pretty old classical results say that there is a different kind of bifurcation structure. And in general, I say that this propagating bubble is much harder to have intuition about. So this is a strength of the driving flow parameter here. I'm sorry, I don't mean the axes, versus a speed of the bubble. But we get a sequence of different steady solution branches. These are the solutions of the actual model. So the only one that's stable is this one that looks a bit like an egg at 0 flow rate. It's a bit pointy at the front. As the flow rate increases, it gets more and more symmetric. This is symmetric, kind of up-down, not back to front. It's nearly stable, but according to the model, there should be a sequence of other steady solution branches. And the challenge for the experiments is to see if we can find these, which is, I think, actually one of the risks is that they're not there, and they're not where we think they are. Maybe they don't exist. Are they an artifact of the model that we use? That's a nice question. But I think for Sammy, the stationary bubble problem, I've argued using symmetries and thinking about what should happen, and I have a lot more confidence in that. Okay. So what do these problems have in common? Well, actually they're both in the same experimental setup, which is a good thing. They're both flattened bubbles at really low Reynolds number. And what that means is that in terms of kind of the physics of what's going on, the only thing we need to keep track of is the interface shape. So if you were trying to control the transition to turbulence, which would be a fantastic problem, you'd have to somehow image the whole flow field inside your fluid. But here, because of the structure of the flow, if you can image the shape of the bubble, you're doing pretty well. And because it's flattened, the shape that we see from above is what we want to see. So we have a good chance of being able to use feedback control. Okay, they've both got non-trivial, unstable, steady state. I'd like to find. We do have more intuition and symmetries for the stationary bubble, one in the straining flow, than the moving bubble. So I'm going to try and present both of them as we go. And in the straining flow experiments, everything we do is based on physical arguments and hand waving, plus experiments. Whereas the moving bubble is simulations and how much more can we do if we have a model that we really trust for our system. Okay, so a little bit of feedback controls. This is maybe the kind of similar diagram to what you might have seen last week. So the basic idea is we choose some inputs that we're going to apply to the system. And the way that I'm going to deliver feedback control is injecting fluid. So I have injecting fluid to drive the flow, and then I'm going to suppose maybe some other places I'm injecting fluid that I can choose, and I can inject or withdraw fluid however much I like. But we're just injecting mass, and that's pretty good in this system because it has, we don't need any new physics to explain what's going on. We've just got more driving flow. So we have some inputs, and we need to choose what they are. And the way we do that is we observe what the shape is, use some rule that we just make up, and how we make that up is difficult, and use that to keep applying in this continuous feedback loop. Okay, so I can write this down in maths very easily to say, okay, my amplitude of actuation A, my injection amplitude, is, okay, we have a minus for historical reasons, some linear operator on the distance between the current state of the system and my target state of the system. And if I am genuinely writing this down, I guess I'm assuming in my maths that we can view everything instantaneously, perfectly process it, there's no delay, there's no noise, we can view anything we want to. Okay, that doesn't happen in the experiments, but it's a good start. Okay, so what is A? Well, I'll show you how we're going to inject fluid in just a minute. What is X? X has to be the state of the system, so that's actually just the shape of my interface. We'll see that in a bit. It needs to be the information you need to specify initial conditions. So anything that you can derive from that is fine, but you need anything that's non-linear or has time derivatives. How do we choose the operator K? Well, in order to make it stable, but we'll see how we might do that. And then at the end, how do we choose these xt? So what target should I choose? Well, if I'm controlling to a uniform film, this is like the state of uniform film. If it's a centered bubble, it's the middle of the channel. But if it's one of these branches that I'm guessing exists, but I don't know where it is, it's a bit more complicated because I'm controlling to something that I don't know. And we have to think about how that will work. Okay, so just how does the system setup work? Basically, as this bubble propagates along, this bubble is moving, I inject fluid at just 2 points on either side of the channel, and I can pick what those amplitudes are. So I should say that in this moving bubble experiment, the bubble is moving, and in the maths, it's beautiful and lovely. You can say these injection points just move with the centre of mass of the bubble. And the analysis is so much easier when that's the case, right? That is the case in the experiments that we had for the bubble and strength flow, which is one reason to pick it. Not so much in real actual experiments, and then we'll be thinking about having an array of injection points instead, which also has its own beautiful mathematical complexity, but we can do much more in simulations. Okay, right. So I have a bit of a mash-up between PDF and PowerPoint here, and I'll have to explain the video and then play it. So we're going to see lots of videos like this. This is the moving bubble. So what we're doing is picking the initial condition that's a stable propagating bubble. And what I would like to do is to get from that bubble to this red dashed one, which is the next branch solution at the same flow rate. If I start off by just, what these circles indicate is the strength of injection that's happening at that point. I'm going to start by just injecting some fluid there at a constant rate. What would you do if you were a bubble? Well, hopefully something like this. As in not very much. You move away from where the fluid is injected. That's what you'd expect. And it reaches some new steady state and it's a bit perturbed like that. Obviously it doesn't get to where I want it to go, because that would be too easy. Right. Okay, so a little bit about how we might think about doing feedback control instead. So if I pick something constant like that, it's never going to get me to where I want to go. Okay, a little bit of analysis of this moving bubble system. We've talked about how a zero Reynolds number in 2D, it's just the shape that you need to look at. And we can observe this. Maybe this wasn't the usual slide. But I'm going to just write my kind of generic governing equations in the form of some function of the state vector and its time derivative is 0. Because that's how it comes up in UMFLIB. Okay, and then we can look at linear stability of a steady state. We get a nice little generalized eigenvalue problem, solve it, plot the eigenvectors. And what we find is that for this, the state that I want is unstable to two eigenmodes. One of them is symmetric, and the other one is anti-symmetric, which is nice. It means they're at least orthogonal to each other. Not to all the other ones. We don't get enough analysis for free here because the bubble isn't a circle. Here are some shapes. And we can also do some linear algebra to set up a control problem. Okay, so now I need to say, what are my governing equations if we have these injection amplitudes as well? Because it's zero Reynolds number, we don't have any time derivatives of the injection. It's just the only time derivative is of the interface shape. So we set up this eigenvalue problem, and this is what you get. We have a mass matrix, a Jacobian, and then we have B, which describes how the injection affects the system. K, I get to choose. And I want to choose K so that all of the eigenvalues have negative real part. Okay? It doesn't really bother me how negative or where they are. They just need to be. It just needs to be stable. It doesn't matter how stable. So that means that we could think of different ways of defining what the optimal K might be. But there should be a huge class of operators K that still makes it stable. And that also means that if my model is a little bit wrong, and I pick something and I think it's way over here, and my model's a bit wrong, so it's over there, it's still stable. And that will do. Do some linear algebra, which I won't subject anyone to. And we get that this K acting on the interface shape could be written as kind of a weighted function around the interface of the radius of the bubble relative to its centroid minus the target reference shape. And these weighting functions F kind of represented by the red and blue, so the actuators on each side and reflections of each other. It's not very illuminating, except maybe you can see that what's going on at the front of the bubble is a bit more important than what's going on the back. We just do some linear algebra. Okay. So let's see an experiment. Sorry, not an experiment. A simulation. So start from the stable state. Get really quickly to where we want to go. So I'm allowing the bubble to move down the channel in a way that reflects how it should be moving. And you can see it doesn't need to move very far to get to the other state. And those injection amplitudes decay super quickly. They're very large to start with, and then they decay to 0 exponentially, which is perfect. So we have optimism, though this is a very idealised setup because I've got these moving actuators in a model where I know everything perfectly that we can stabilise the problem quickly if we like. Okay, and we can do this for some different initial conditions. And in general, we get to the same unstable steady state at the end of it. And in each case, the injection amplitudes, which I'm plotting on the left, decay to zero as time increases. And the thing that's really actually important is that this actuation amplitude does tend to zero, which means that the control is non-invasive. So at late times, the control amplitude is virtually zero. Right, so the control has to be omniscient. It has to always be, maybe that's not the right word. You always have to watch, and there's a bit of noise, whether that's numerical or an experiment, move it back again. So you have to always watch this thing, but the actual amplitude is essentially zero. And what we want to find are steady states in a system that doesn't have any control. So we really do want the non-invasive case. If I needed to have like a non-zero average or a non-zero control to get me there, that's not the same as my original system. So to start with, it's not the same. And as time goes on, it is the same as the one that we have. And this is only actually possible because this shape that I have here is a steady state of the system without control. And that's really the trademark of what we're trying to find, states where the control can go to zero at late time. Okay, what about some nice experiments here? Okay, so we supplement our actual physical experiment. These ones in the middle are a driving flow rate, and then we're going to add 2 channels on each side that inject fluid just for the purposes of feedback control. I don't think they're labelled, but that's probably my fault. Yeah. Okay, so we said that this first branch of the bifurcation diagram for the bubble and straining flow was just unstable to translating the bubble. And the way that you'd set up a feedback control is to say, if it moves over this way, inject fluid on that side to move it back again, and vice versa on the other side. So we can pick, and we know that we need to move it towards the middle of the channel if we set this up perfectly level. So alpha is just a constant, which we choose heuristically, which means Samuel tries some different values until it moves to the middle of the channel. Okay. And that's actually all we need to do to get most of that first branch, is to just move it back to the middle of the channel. And here we go. So the bubble starts off, that again. A bit asymmetric, but is moved to the middle of the channel, reaches the steady state, and once it looks steady enough, I guess that's kind of up here. We measure the shape of the bubble, got it on the sand diagram. So we can get like the whole first half of the diagram like this. And in fact, this has been done before in the 80s via roll mill experiments where very slightly different flow, but the general idea. And then at some point the bubble splits, and we know there's a limit point. What else happens? How do we get there? Well, what's next? Okay, so the second branch is still unstable to translation of the bubble in the x direction. The second branch, and it's also unstable to the deformation of the bubble between these 2 symmetric states. So just deformed and even more deformed. Okay, so I can just linearly superpose my linear controls and say, this is the one I had before, this is just controlling the centroid. And then I'm going to have another constant beta times the shape of the bubble minus the target shape. Right, so what do we choose to measure the shape of the bubble? Well, we could do maths. We could set up the same modeling framework. It's sort of satisfying and certainly more accurate to what we actually do with the experiment, to just sort of guess what is happening. So my bubbles are left-right symmetric and up-down symmetric. We're looking at a bifurcation between 2 different sets of bubbles that satisfy that, and they have the same area. So the lowest Fourier mode that satisfies all of those symmetries is cos 2 theta. So we will just guess that if we measure the amount of cos 2 theta in the bubble shape, that will give us a good enough approximation of the bubble deformation. Okay, we can compute it later, that's not actually, it's probably the largest Fourier component, but it isn't exactly. which is probably what you'd expect. The bubble isn't exactly a circle, and the setup isn't radially symmetric. But it's a reasonable guess, and it works. But there's a bit more to do. Okay, so the problem is, here's my nice setup of the feedback controllable. And if I know the shape that I want to control to, if I know that value of m t, I can just go and do this. I can set that up in the experiments and see what happens. But I don't know the values of m t. I can maybe guess it by trying to fit a parabola through this curve and very much hope for the best. But what happens is that, suppose I just pick a value of m t. Right? I pick a target. I don't need to pick a whole target shape. That would be really difficult. The only thing I need to know about the target shape is how much positive beta it is. And that's a single scalar, which is helpful. So if we pick a general target shape or a target measure, and we set A is equal to minus k times x minus xt, what I want to argue is that most of the time A is going to be non-zero. So we're supposing that we've got a good enough stability that it's going to reach some kind of steady state. Okay. So I've just picked an arbitrary xt. If the bubble actually went towards xt, was exactly xt, then A would be 0, and it would have to be a steady state of my original system. So I could only get that if by complete fluke my target was a steady state of the original system. On the other hand, it can't go to a steady state by itself because then A would be non-zero, and it was only a steady state of the original system if A was 0. So it has to go to something else, something kind of in between the target and the actual steady state that it's trying to find. And in this in-between shape, it has a non-zero amplitude control, which we can hopefully measure. Right? But what we really want to do is to find the target shapes so that, or target states, so that A tends to 0 as t tends to infinity, and then that corresponds to a non-invasively controlled state of the original system, which is what I wanted after all. That sounds like a lot of work. It's not quite as bad as it sounds. Basically what we do is we just carry out experiments at some different values of mt, see what happens. If it reaches a steady state, we measure the actuation amplitudes and see whether it looks near 0. Actually, we're looking for a 0 crossing. That's okay. And it's really important that it's just a scalar that we're looking for, not some incredibly complicated high-dimensional space. Okay. Right. I think I might be going to do this a bit faster in April. Did that work? Okay, so this time it's just an experiment under positional and shape control. So you can see the positional control is making it centered, and then we're applying. It's really lucky that this works. Shape control, I'm pretty sure we might get to this. Okay, so what we've done is fixed all of the parameters, the strength of the straining flow, the size of the bubble. A whole load of experiments have happened, and depending on what target state you choose, sometimes you have a large negative injection rate, sometimes you have a large positive. But you can hopefully see that there are 2 points where its data is crossing 0. One of them corresponds to this shape, which is where we were on the first branch of the system, which we actually could get without needing the shape control. We just had to move the bubble to the middle. And then the second point is on this second branch that we couldn't get to before. So what we do is fit a straight line to the points near these 0 crossings and use that to extract a bifurcation diagram. And I did show you a hypothesis earlier. Can't hear it. Nope. Comes back. Okay, so this is all of the data that Sunny ends up with. So we had these points, which are shown in blue here, starting from a circular bubble, moving up towards its limit point. And in fact, the blue points are basically obtained just using position control. Then I showed you actually lots of data on the previous slide, all sitting at just 0.9 in this unit here. And we had two different bubble shapes that were at the same flow rate. And we can get quite far around the limit point to data that we definitely didn't have before. These are actually quite awkward experiments to do. One of the things is that the model is very prone to just slowly losing volume. So we can follow that as a problem. Another is that we seem to get oscillations in the dynamic, which might be to do with delay feedback control. There's another thing that's very specific to this setup is that the bubble just breaks afterwards. Right, so it's really difficult to navigate past these shapes at the top, where you're trying to use feedback control against a bubble that really wants to break if you nudge it a bit wrong. So it's not, in hindsight, it's very difficult to get much further than here. Now, I think everything else I'll show you is a model, but I will show you just a bit of quantitative comparison, because once we've got this far, and I've been talking about modelling moving bubbles, maybe we can model a stationary bubble too. We get, that's this black line. Sorry, it's quite preliminary that I was hacking away at last week to make this, and I haven't quite managed to continue, but what we do have is actually really good quantitative. Okay, so this black line here, we're arguing about tiny errors, and we get a limit point in pretty much the right place. The black curve is curving around and is getting into some really bubbles that are really close to self-intersection. We don't know whether the branch kind of stops where Sammy gets to, because this depth average model that I'm using is throwing away so much physics. In particular, if I have a bubble that's like that one at the top, but even more so with a thin strand of bubble, then you would expect 3D effects to want to pinch that off by something like Rayleigh plateau. And then I might not like it. The things that we had to do to make good quantitative agreement was actually put in a factor of pi by 4, which is a kind of classic thin film correction factor. What you would do classically is say that this pressure jump, or this coefficient, is a function of the local capillary number. Here the local capillary number is 0, the bubble is not moving at all. So you just get the pi by 4 in front of the sequence. And then also doing all of the fizzy bits to make sure these injection points are where they should be and not on the edge of the cell. But we get some pretty great quantitative agreement here. Okay, so that works. It works really well, actually. Okay, and then I'll just talk a little bit about the kind of things that Sammy is hopefully trying to do next. So I started with the bubble and strain flow because it's got some beautiful experiments, and it's a little bit easier to get your head around how that might work. We can do almost the same thing for the moving bubble. This is a bit dense in maths. Okay, so the feedback law I showed you had kind of an MT, which was just obviously a scalar, which is the only thing I needed to know. Here, well, what do we need to know? We need to know K acting on XT. So that is a function of whatever K you pick. But because I've got these two actuators which are set up at the top and bottom of the cell, and they're just reflections of each other, and because the unstable state I want is symmetric, actually it turns out that this thing that I need is just two copies of the same scalar. So it's the same thing as before. We just have one scalar parameter that we need to vary in order to think about characterizing the target state. And then sadly we definitely got into simulations here, but this time if I vary this target shape, bearing in mind that my K is just something that came out of a model. I just did some maths and it said, well, here's the answer. Or a painful process, but what we find here is that, okay, I'm plotting the amplitude of actuation of injection versus the target shape that fits other parameters. And there are three values this time, potentially more actually, there should be a whole sequence of them where it crosses 0. So one of them corresponds to the state that was stable before, one of them corresponds to the state, the double tip state that we've managed to stabilize by feedback control. We also have a triple tip state. That's not stable. it just looks like it crosses as projection, there's no way it does. And then I guess the fourth tip one is somewhere around here. It's kind of a coincidence that these two things are both stable under the same choice of k, though it's, I think, mainly a function about where we put the actuators in this. Because if you stare at this for long enough, it's like this shape is almost independent of k. Because I can just think of these as, well, suppose I completely changed my experimental setup and had a fixed injection amplitude. Well, at least in numerics, I can just solve for the steady state subject to that, and then I can infer what this one is, or vice versa. So a lot of what the feedback control is doing is sort of changing what we're setting, what we're allowing to be a function of what, without necessarily changing the physics in the system. Okay, so what I want to do, I could do lots and lots of experiments going on here to decide where zero crossing is going to be. Hopefully, if we can make that work in this experiment. We could do a little bit more than we do in the experiment. So one thing that we could do is, what Sammy had was lots of experiments, and then he kind of went back and refined. And if you have an experiment that will sit happily forever, our channel is perhaps not that long, you can couple these things together. So here's my feedback control law. So that's got MT in it. And then I can say, but actually, I don't know MT. I want to choose it so that the actuation amplitude is 0. So let's make MT vary slowly in time as a function of the currently observed actuation via a constant I call beta, which is not helpful, it was something else before. And actually what we can do here is just pick some kind of arbitrary shape, which might be a circle, and depending on what values of beta we choose, the system either goes towards this one or this one, and I suppose I should explain that a little bit more, which is if this system is going to reach an equilibrium, it's got to have this thing, a plus plus a minus is equal to 0. And if you just assume that the setup is symmetric, which it is because of the feedback control, that means a plus and a minus are both 0. So the system is non-invasive in equilibrium. So I can do lots of experiments. If they reach a steady state, it has to be a steady state on my bifurcation diagram. On the other hand, it's probably more complicated to set up. It takes quite a long time to evolve towards these steady states. Okay. We are totally going to try this. Okay, but there's that issue of the moving actuators, which is pleasant in maths, but not really. Right. So what we're going to do instead is have a whole sequence of actuators. And this gets more complicated. It really does. Okay, so the steady states themselves are time invariant. The steady states in the absence of control don't care where the actuators are because they're not doing anything. But if you think about the linear stability problem, all right, so this is properties of, with respect to moving frame, properties of the steady state, plus B of t is how the actuators affect the bubble shape, which is definitely a function of where they are. And then my k could be a function of time as well. That's pretty ugly. Stuff you can do that would be incredibly efficient if you wanted was to say that k is a function of time. So how I react to the bubble shape depends on where the bubble is. There is a problem with that, which is I still don't know my target shape. I wanted k times the target. So if k is a function of time, instead of trying to seek mt, which is just a scalar, I'm now seeking an unknown function of time. Definitely worse, don't do that. So the way we do this instead is to actually keep k constant, which was set up for just a single pair of actuators. But as the bubble moves along, we just pick the ones that are sort of ahead or close to where we want them to be, and then switch to the next one, and then switch to the next one, switch to the next one. That's definitely easier for control-based continuation. And we can do some maths to calculate how the stability property depends on the distance of the actuators ahead of the bubble centre of mass. And what you find is that there's some kind of calculated movement for d equals 1, but there's some window of spacing that I can choose where the eigenvalues will all be negative. And so at every instant the bubble is being stabilised. Not sure whether I've got my next video. Okay, here's some painful maths. Are you ready? Okay, so because it's a linear time periodic system, it has linear system with time periodic coefficients, you should use concave theory to look at the stability of this system. But handy thing that I did was actually set up K to only act on the two eigenvectors that are unstable. One of them is symmetric, one is antisymmetric, so they don't interact with each other at all. And that means the eigenvectors are constant in time, and you can just consider one at a time. Okay, so if you go back to a scalar system with this property, you'd say like d whatever by dt equals y is a lambda of t times y. This thing you can solve using an integration factor. And what that really says is that we have a periodic function of time times an exponential, and the thing that goes in the exponential is the average value of that eigenvalue. So what's comforting is that it's the average stabilising effect over one period that tells us whether it's going to grow or decay, which is nice. It means I get a slightly bigger window. Plus it's just really nice maths. And if we do a couple of experiments here, numerical experiments, we have one at the top where I think the actuators are really closely spaced together and it decays, but also we can get along with things that are a bit larger here. Okay, so you can, I think, see how this switching is working. So it's just one pair at a time that's doing everything. The actuator amplitude isn't monotonic. But that's okay, it's still zero if we wait long enough. And so what Sammy is trying to set up now is this kind of thing, which is interesting and complicated, and it's fortunate that we found really well-spaced actuators because they are a pain to set up and quite expensive as well. So but not as bad as we thought they might be. But we have a switching system which needs to work. Okay, I think I'm pretty much nearly finished, but just to say a little bit of math that you don't need to see very much is that if we had perfectly moving actuators, as I said, that we get exponentials again. That's this line in blue, and we get that. You see the numerics get a little bit wobbly because actually the problem when we have a fine mesh and small amplitudes is that every time I get a new mesh, the steady states move around a little bit, so it's not decaying exactly to zero anymore, which is a right pain in the neck, but actually that's kind of the whole point of the talk. Whereas if I have moving actuators, we get a periodic function times an exponentially decaying envelope, and we're looking at that kind of log scale here. The yellow one, which is quantity spaced, actually the amplitude increases in time, but still over at some instance, but over every period it does decay, which is nice but complicated. And maybe don't try this at home. Okay, what happens when we set up the kind of control-based continuation thing? So what I want to do is to say, I'll do lots of experiments at different values of NT. There's too much information on this flat line, sorry. But if you look on this picture here and ignore the bright blue line, what we're seeing is different values of NT. And instead of going to constant values and then we're looking at that crossing zero, instead we get kind of oscillations with a non-zero amplitude and a non-zero mean. And that's, it turns out, what you would expect in general for on a dynamical system with these time-varying control properties. So it's just really complicated. You add some noise as well and find out local experiments, and it's getting quite painful. And so the kind of zero crossing that we're looking here is instead of just getting a line, we're looking at oscillations whose amplitudes vary, but still does have a zero crossing in the middle of it. And if you're feeling super brave and you just make MT to be a function of time as well, you get these lines shown in blue here, which do eventually home in on the shape that you want if you have enough time. And you trust that nonlinearities won't cause something bad to happen in your experiment, which I guess is totally up for grabs. Okay, I think I've just about finished. I have way too much information here. Okay, so firstly, if you know what you're trying to get to, feedback control is really helpful at getting there. You could use a complicated model or a really simple model, and so long as it gets to where you want to get, you know you've done it. It is useful to have mathematical models, especially if you don't have symmetry arguments to rely on. They're the best ones. Ones where you say, if I push fluid in here, the bubble will move over there, is a good start. But with things like the moving bubble, I find it very hard to have intuition about what you should do. It's really helpful to have a mathematical model. That's actually quite important because most of the time your model won't be very good, but it might be good enough to give you effective control. And then if you combine that with something like control-based configuration, so long as it manages to kind of stabilise the equilibrium states, we get the observations of what exactly a steady state is that's non-invasively controlled from the experiment. And we're just using control as a tool to help us get there, which is what I wanted to start with. If you're feeling really brave, you can get machine learning to do that. Say, I don't really care what my computer is doing. So long as when it gets there, it's steady and non-invasively controlled. And maybe I don't need to know what weird thing happened in the middle. And the information that I'm getting is just the cool observation of being able to see all the different things that your system can do, which is nice. So we can use control-based continuation, which I think should have more application in mechanics than it does, to detect steady states, and that's really trying to do kind of control-based continuation in general is trying to be the equivalent of numerical continuation methods, but in experiments. So what would you like to do? Solve the steady states. You'd like to do arc length continuation. You'd like to do bifurcation tracking. You'd like to find stability properties. That's not very easy. So in principle, you'd like to do all of these things. This is probably the simplest one. But the more that you have a low rank control, or symmetries in the system, the easier it gets. I've definitely shown you effectiveness in real experiments. We are optimistic, and I hope that optimism is well founded for the moving bubble, which I think would be really fun. Okay, thanks.
Any questions?
There was when you were showing like the convergence to the exponential with some oscillation, there was like some ripples in one.
Yeah, I think that's meshing.
It's meshing, okay.
I think so. So I have some other numerics which are on like a fixed mesh, and it doesn't have that. So
Okay.
it's really awkward to do because firstly, don't plot anything on a like semi-log scale because it gets really awkward. But actually, it's only going to be exponential if you've got your target shape exactly right. Because if not, then it's going to level off at something, and that's you can see that it's trying to level off at something. And I think the ripples are just that as things get smaller, those ripples get bigger. It's an absolute pain. But yes, I think that's mesh sensitivity. It's not an additional timescale.
If I remember well from the four-roll experiments back in the 80s, I haven't done any of them, but I know it's an open flow arrangement.
Yeah, it's
The
not.
bubble doesn't seem to be translated. It just deforms a little bit.
But is that not because they control against translation?
They do not control it. So I wanted to say regarding your model, do you say anything about the volume, whether it's the volume of the bubble, whether it's
It's
fixed?
fixed.
Whether it's fixed. Do you impose that?
Yes.
Okay. And then regarding the P, the mode that corresponds to the translation, I know that in axiomatic geometry sometimes this is neutrally stable. So,
Okay.
So
It's
what?
definitely unstable here because we see it in experiments and it is.
No,
It definitely is.
in experiments, yes, but in your theory as well, I guess.
Yeah, I think so. Yes, I'm pretty sure.
And you only get asymmetric shapes that move eventually, or symmetric shapes as well.
I think it depends how you measure them, but the steady states are all symmetric. And I guess the way it can move would be a superposition of translation and potentially deformation. So it could be symmetric and then move symmetrically and then slowly become asymmetric because the flow isn't symmetric as it moves. But I'll have a look.
I'm a bit
Yeah.
confused regarding the
Yeah.
translation part of that.
I'm pretty sure about what we see because it's just based on symmetry arguments, so it can't be that problem. Like, but I'll have a look. But yes, it's actually quite a different setup to the full roll mills because it's in this heat shore cell. If we had rolls, nothing would happen. The walls would just completely screen the effects that we have to inject fluid instead.
Alice, you showed some integrals of r cos 2 theta and other
Yeah.
integrals with respect to theta. Do you care about where the origin of your coordinates is, or does it not matter?
So we measure relative to the centroid of the bubble.
Okay, so
Yeah. And that's, so for the propagating bubble, that's kind of the right thing to do because I don't care where the bubble is, I just care about its shape. But there's some real fiddliness about the y coordinate. So we put the y coordinate on the centre line of the channel and the x coordinate with the x coordinate of the centroid. And then for the straining flow one, we measure the radius relative to the centroid, but we measure where that centroid is. So we do one set control based on where the centroid is, another shape on another shape control based on the radius relative to that centroid, which is enough.
so it does matter quite a lot to get that origin where you want it to be.
Yeah.
Okay. Can I ask a related question? I couldn't tell whether you need to care about the volume of the bubble. Is that changing in time? Or
Yes,
is it
and we care a lot.
so it's more complicated.
It is, so it's always slowly changing, and the way that Sammy sets it up in experiments is to start with a bigger bubble and wait, actually he controls it to the right place, and then wait until it reaches the volume that he wants, and then watches it over a minute. And it changes by not more than 90% over that time.
So yes,
But it is fiddly. So he's had to pressurise the channel in the first place in order to be able to inject and withdraw fluid with the setup that we've got.
wow.
But yeah, so there's a whole load of physics that you can just ignore in maths that comes back to haunt you.
I take my hat off to
Yeah.
your team. Yeah.
But I mean, another, and I'm really pleased how well the numerics and experiments agree. But actually, it's not necessarily obvious that there are definitely steady states in the straining flow system. So if you're the bubble sitting here, sort of pancaked, it could be that the films are just getting slowly thinner forever. So there could be a slow flow in one direction while it's relaxing in another. So that's harder. In the moving bubble system, it's sort of easy to convince yourself that because the bubbles are always, sorry, the films are always being created and destroyed, that there's a balance that sets up how they work. Maybe that's more independent of time, perhaps, than something where maybe the films are always slow throughout. But it turns out not to matter too much, depending on what time scale you're looking at.
Thank you.
Can I just ask a question?
Yeah.
Well, supposing there was a hot bifurcation in your
Oh, yeah.
system, could you, and there was an unstable periodic
Yes.
orbit, could you try and control sort of?
So people do, and the kind of controls that are used are actually more like time delay feedback control. So instead of, so you could compare it to like a made up function of time that's like what the shape is over a function, over a whole period. But you can also compare it to what the bubble was doing a period ago. And then you have to get the period right, that's the parameter that you vary. But the idea is that if it's exactly periodic, it's doing the same thing as the period ago, so you're not doing any invasive control. But you would need to think about quite carefully, I guess, how to set up your feedback rules so that it became more periodic as a function of time. But yes, it can be done, but you would use a different control. But it would be cool. It would be nice. We have enough problems as it is, so it's great, but I don't think I should get that into myself.
So why did the number of unstable modes go up by 2 at a
Sorry? Why?
time? Yeah.
I don't know.
I mean, is there an asymmetric branch in between?
Not that I know of, but I don't know that there isn't. I've tried. I was like, I'm using control-based continuation to try it from but I can't. I guess there's a selection problem with zero surface tension, which is very large flow rate in this limit, but we're not working it there. So I guess that would be the place to look, but I don't know. People have looked and have not found, but that's quite a long way off.
Okay, maybe we should draw things to a close. Thank you, Alice, again.